a rainy day. Yeah, you have plans, but let's be honest, an excuse to stay curled up at home is a win. You got your fuzzy blanket, a mug of hot chocolate, and this YouTube music station. But what if it doesn't have your rainy day favorites? We got you covered. Get YouTube Music Premium and listen to playlists made for every vibe. Start a trial on us in the app or online. Terms and conditions apply.
All right, I think we're about at 5 minutes to start. Can I get a quick sound check here? Anybody hear the music? If you hear it, someone post a quick chat message. Hello. Thank you, Melody. Cool. All right, so we'll start in about 4 minutes then. Get some water. All right. Well, I think we can start with the end of the song. Maybe not. Maybe it's got a few more minutes. But all right. Okay, Google, stop. All right. Hello, everyone. Welcome back to our live lectures on sorting. This would be lecture 11, which is on Quicksort. But of course, I will go and kind of finish up some of the elementary sorts discussion that we started in the last lecture. So we'll go back and go over counting sort before we dig into Quicksort today. But I'll start with the main thing to remember is that Quicksort is a single word. It's actually the name. It's a single word, not quick and sort separate. It's the whole name. It's Quicksort. And then similarly, it's merge sort. It's a single name. But again, before discussing that, let's go back to elementary sorts a bit. And of course, hopefully you're well along your project too. If you recall from the last lecture, we had that all elementary sorts, for the most part, worst case is n squared, and actual also average case is n squared. We talked about considering number of comparisons and then potentially taking a non-adaptive version of an elementary sort, making it adaptive to either remove the number of comparisons or remove the number of swaps, which is what we also care about with regards to performance of these elementary sorts. Now, in any average case that we're considering, we're not showing the math because it's really complicated, but when we say average case for the input, we're referring to the fact that we're assuming that the numbers in the input array or vector are uniformly distributed. Okay, and then we did talk about the fact that there are some elementary sorts. Oh, yes. Okay, so there is an announcement that we have. Very good point. Do fill in the form for your time slot to take the midterm exam. Very important. So that's a very good announcement. I don't know who's from staff on the chat, but thank you for reminding me that. So we also discussed this notion of the fact that given, say, an almost sorted input to the algorithm, in this case, these elementary sorts, you could get better performance out of them, right? So let's actually formalize that with this notion of an inversion, which is a pair of keys, right? Remember, keys is whatever we're comparing in our sorting algorithm. So we're going to define an inversion as a pair of keys that are out of order, okay? So if we're looking at it per item basis, then we can determine the number of inversions, okay? So for each item, you can determine the number of inversion, which would be nothing more than the number of items to the left that are greater, right? So you look at an item, and then you basically iterate over all the elements that are to the left, right? If any of those items are greater than the item that you have been looking at, then that's an inversion. Okay? And then, of course, but when we do that for each item that we're given as input, or each element, then we can determine the total number of inversions that we get in the input array. Okay, so this gives a sense of pre-sortedness. Okay, and what we alluded to last time, which we'll kind of summarize in the next couple of slides, is that some sorting algorithms, even if they're elementary sorts, they do perform better on this pre-sorted, call it, or almost sorted data. Okay. In fact, oftentimes, if the array is small enough, they actually perform better than high performance sorts, as we're going to see today. Okay. All right, so the way that we're going to discuss this is kind of give an overview of the property, followed by kind of an interpretation of said property. So the property is that insertion and bubble sort use linear number of comparisons and swaps for data with a constant upper limit on the number of inversions for each element. Okay, so that last phrase is basically saying that they effectively perform in linear time if the input array is almost sorted. Okay. So that's basically the interpretation you see below. Insertion sort and bubble sort are efficient on partially sorted data when each item is close to its final position, right? Because that's how we're basically defining almost sortedness by our previous definition of inversion. Okay. All right, so that's basically a summary of what we saw last time when we were looking at these algorithms in details and the code, and we kind of did some micro optimizations. Then we have another property, which is insertion sort uses linear number of comparisons and swaps for data with a constant number of elements having more than a constant number of inversions. Okay, so that's a long sentence. But in other words, it's a small number of elements that are very far from their final location. Okay. So the way to interpret this is the fact that if you're basically starting from, say, a sorted array, so your current array is very close to sorted, then if you wanted to add a new item, then it's better to do it by way of an insertion sort. Okay. Basically, it will run in linear time, which is if it's an array, any insertion and to keep the sorted property of the array would constitute linear time, because you'd have to maintain the sorted property, you might have to insert in the middle of the array, which means that you have to shift everything. Okay. All right, so that's insertion sort, or a bit about insertion sort. And then selection sort runs in linear time for data with large items and small keys. Okay, so if you recall, this is why we want to have a trade-off between number of comparisons and number of swaps, depending on the context of what you're looking to sort. It might make sense to reduce the number of comparisons as opposed to the number of swaps or moves of the elements in the array. So an example of that is there if you needed to sort 1 megabyte medical records by a single integer, which is social security number. So the interpretation of this is selection sort is expensive in terms of comparisons, but cheap in terms of swaps. Okay. So it is on the order of linear in the number of swaps that you would need to make. Okay. So much better than, say, bubble sort. All right, so that's basically a summary of kind of, the optimizations that we looked at for each one of these elementary sorts. Again, the ones that we have discussed so far: bubble sort, selection sort, and insertion sort. Let's lastly look at counting sort, which if it's actually a linear time sorting algorithm. Okay, so as we're going to see, but you are limited in the cases in which you can use a counting sort. Okay, so let's say in this example that we're showing on the slide, you would want to, the inputs in which you can use count and sort is when you have a limited number of different keys. Okay, so here's an example where we have, there's 13 total, but you see that the keys are repeated, right? So D, which we're assuming is an input key, that we're sorting over. And then F is repeated, and so on and so forth. So the number of distinct keys is smaller than the number of total items that you're looking to sort. So what you're going to do is you're going to have a first pass right here, where you count the number of items that match each key. Now the idea at that point is to not copy data, just count it. So this is, as you can imagine, a pretty simple loop to come up with. The second pass is to compute offset, where each key would start in sorted order. Okay, so you can manage this as a second loop that, given the counts from the first pass, I can figure out the offsets at which the new subset of data with a different key should start. Okay, and we're going to see an example of that in the example code in the next slide. And then only on the third pass would you actually copy records into an output container. Okay, and so each key or each data that has the same key would be grouped together in the same subsection of the array, all in sorted. Okay, so now be careful when you're looking to actually implement this algorithm. There are, for example, another algorithm that is similar, but it's not exactly the same as this one. Is bucket sort. You might have heard of that one. So the idea is that you should have a limited number of buckets in which you can place the items, such as, say, the number of possible birthdays, which is 366, number of possible class standings, which we're saying it's 4. I mean, if it's 10, it doesn't matter, as long as it's a countable limited number of distinct keys. Okay. When you actually implement, make sure to, int max is not interpreted as limited, and it's actually, it changes architecture to architecture. So, there is an actual limit implementation-wise on what you can use to kind of count the number of buckets that you're going to have. All right, so let's look at example code for this. So we're basically declaring our output here, which is input size. So we're saying this is n. Okay. And then we have our counts. So we have a separate vector, which is counts. Okay, which is on the order of max, where max is some integer. So this is the first pass is lines 5 and 6 right here, right? So this is when I compute frequencies for each key. Then this is the second pass that we were talking about. Notice that the first pass is going to be O of n, assuming that, again, input.size is n, right? So this is O of n for loop. Then the second pass is just going to be O of max, whatever that size is. And of course, again, this is an integer, and you need to make sure that it can't be millions, right? Because then that's pretty large. And then the last pass is when you actually do the copying, which is also O of n time. Okay. So we basically have a linear time algorithm for sorting in this specific context. Of course, a big additional issue here is the fact that it's not in place, right? So we are creating a separate output vector or array that we're at the last line here, line 13, we're going to swap such that the input container now has whatever the output was at the end of the closing curly brace. So we're incurring O of n extra space. Okay. And of course, if you should watch out if max is on an order that is greater than n, then, that would be terrible. Okay. Definitely in those situations, you wouldn't want to use counting sort. You get a benefit in counting sort when, say, the order of max is much, much smaller, okay, than n. All right, so that is counting sorts, and then following us, this is a summary of elementary sorts. Basically, all of them, all the first ones that we discussed last time are O of n squared. So that's bubble sort, selection sort, and insertion sort. They are in place. So if you recall from the code that we saw last time, we never had to create a separate vector or array to do anything. We did have to do that for our counting sort just now. So we do get the benefit of linear time for the algorithm, but it's not in place, so it's extra space. And so as we discussed in the previous couple of slides, some sorts execute more quickly in special cases. All right. So in project 2, you will have to use STL sort. So get familiar with it. Basically, you give it a range being defined by the start iterator and then the end iterator, or whatever you want to call it, lower bound iterator and upper bound iterator. So that specifies the range that we are going to sort over. And then you're going to give it a functor for how to compare the elements that exist in whatever container. Okay. So this is, to remind you that STL sort is going to, if you don't give it a functor, it's going to default to try to use the less than operator. So either you overload that or C++ will assume that it's overloaded. Otherwise, you'll get a compile error. Okay. All right. So that's elementary sorts. So now we're kind of done with elementary sorts. So let's basically start with the rationale for why we need high performance sorts. One of the issues in elementary sorts is the fact that we're basically comparing each pair of elements in the array. Okay. Well, it might compare every one of them, but what we usually get is like n squared divided by 2 on the average case. But again, O of n squared. Because if you recall from your 203, if you were to count the number of distinct pairs that you get in a set, that's going to come out to be O of n squared. Okay. They also often move elements one place at a time, which can be rather inefficient. If swapping or moving elements around is our sort of top priority to optimize, then we spoke about the fact that selection sort would be an ideal because it only moves exactly what needs to be moved, right? When you're doing the sorting, okay? And there's no other waste in terms of moving elements around like you have in insertion sort, and not waste, because the fact that you're doing those moves or swaps are getting the actual element closer to where it needs to be, but you might have to do 2 or 3 swaps before the element gets to its rightful place, whereas in selection sort, that's always once. Okay? So these high-performance sorts basically attack these two problems, right? And these high-performance sorts are not by any means trivial. If I think about it, I don't know I would ever come up with Quicksort as a sorting algorithm if I were given the task to do so. Smarter people have come up with these algorithms. They're tried and true. So let's learn what they do. Okay. All right. So Quicksort, some background. We would say it's easy to implement. All right. Here, sort of a caveat on what we mean by easy. So there's not many lines of code that you'll need to implement Quicksort. Okay. Now that said, there are very easy ways in which you can introduce bugs into the algorithm. Okay. So while it's easy in terms of not requiring that many lines of code, you do have to be careful implementing it. Make sure that you're basically keeping track of the proper bounds and increasing indices, i.e. moving pointers to the data in the correct fashion without any bugs. It works well with a variety of input data, so that's really good. That's what makes it rather practical to generalize, right? That's why it can be the algorithm of choice for STL, because STL doesn't really know the details of, say, the elements that you're trying to sort, and so this Quicksort works well on average and in practice with many different types of elements that might be looking to be sorted. So that's what makes it real practical. It is in place, okay, as far as additional memory. But there is something that we'll need to keep in check, and that is the fact that it's a recursive algorithm and therefore requires stack frames, okay? So we'll talk about that in a little bit. All right, so Quicksort is a divide and conquer algorithm, okay? And if you wanted to describe, this is kind of a one-slide description of Quicksort, okay? Really, you don't need any more details than this to describe the algorithm. Okay, so here it goes, but of course we'll talk a lot more details about this in the coming slides. So you have your base case, which is the input array or the range that you're looking at inside of the array. Is of length 0 or 1, and so therefore the input is trivially sorted. Not much that you need to do. That's a base case, real simple. Now you do have an inductive step, okay? And that is that what you're going to do in whatever the range that you're given as input, you're going to guess an element, okay? And this guess is going to be very important, okay? But for now, just think of it, choose a random value that exists inside the current range that I'm considering. Pick that and then partition over that element. Okay, so what partitioning means is that that element, it's going to exist and we're going to put it somewhere in the array or the range that we're considering such that all the elements to its left are going to be less than that current value, and then all the elements to its right are going to be greater than that current value. Okay, notice that this says nothing about all the other elements that are to the left of this value. There's no particular relationship or constraint on there, right? So an example of what you can have as a partitioned array is that you have, say, 1, 3, well, let me not start this sorted. You have 1, let's call it 5, okay? And then 2, 7, and then 11 and 10. Pick that example. Just made it up, right? Here, this is the ELT that I'm referring to here. If you can tell what I wrote there, which is, sorry, let me rewrite that. ELT. Okay, so in that case, 7 is ELT, right? And everything to the left of 7 is less than 7. Everything to the right of 7 is greater than 7. Okay, let me add commas here so you know my handwriting. It's not the best. So notice that here there's no notion of this subset of elements being sorted in themselves, right? So it's out of order to like 5, which should be, it is greater than 2, so it should be to the right of 2. But 2 is not our ELT. It's not our ELT right now. Our ELT is 7. So with respect to 7, the partition is still satisfied. Okay? All right, so in the coming slide, we're actually going to look at a code implementation of the partition function. Actually, we'll see 2 flavors of it. So once you have this notion of a partition, then all you need to do is say, all right, I'm going to recursively sort, okay, the left-hand side, and that is the left-hand side that comes from the partition up here, and then do the same thing on the right-hand side, right? So this is the conquer in divide and conquer, right? We're going to do the same process on the left-hand side and the same process on the right-hand side independently in 2 separate recursive calls. Okay? And that's it. That is Quicksort, okay, conceptually, of course. So let's look at actually, before I continue, let me see, are there any questions? Well, I know that we have staff on there. Is merge sort a type of quicksort? No, it is not. It is a completely different sorting algorithm. In fact, merge sort is going to be the topic for lecture this Thursday. Okay, so we're going to discuss it separately. Okay, so I think there were a couple of questions about counting sort, but we have it covered in the chat. All right, so I'll move on. All right, so let's look at what a potential implementation of Quicksort would look like. And this is assuming that we have a simple partition function that we're going to talk about right here. So, but for right now, treat this partition function as a black box, right? We're assuming that's correct, and it does effectively, given some pivot, which is what we're going to call that ELT variable that we were talking about earlier. Okay, we're going to give this a name and call it a pivot. Okay, so we're basically going to assume partition is a black box, which is going to select a pivot and then do what needs to be done to make sure that we obtain the proper partitioning. And then it's going to return whatever that pivot was, whatever was actually used during the partition process. Okay, so this right here takes care of the base case, right? And this would be the first recursive call, and this is your second recursive call. Okay, the first recursive call takes care of doing all the same stuff, right? It's recursive on the left-hand side, so from left to pivot, and then the second recursive call would be on the right-hand side, right? So this is left-hand side and right-hand side, if you want to trace back to the previous slide. Okay. All right, so one quick note about line 6, okay, is that line 6 is tail recursive. Can anybody actually, a good sort of refresher from 280 or what actually earlier lectures in this course as well, why is line 6 tail recursive? Can anybody answer that in the chat? I think, Eden, because it's the last thing you do. Yep, very good. And I think Eden was also had the same idea. It's basically the last line in the function, right? So after that, it's just a closing curly brace. So therefore, the recursive call does not need to remember anything. Contrast that to line 5, where we're still not done. We still have to go through line 6 in order to finish that recursive call. So whatever happens in line 5, the stack frame will still need to be there in order to remember what happens at line 5, right? When it comes back from the recursive call. But not line 6. And if it's line 6, then you're done after that. There's nothing to remember when it comes back from the recursive call. So that's why line 6 right here is tail recursive. And this one right here is not tail recursive. Okay. All right, so we'll come back to that point in a little bit. How do we actually implement this partition function? It's actually often when we have been doing these lectures live, back in the day when we were doing these lectures live, like in person, I was always really interested in making this an exercise, but can't do that here. Really wouldn't serve well. And that is like, if I told you to implement a function that performs this partition, how would you go about doing it? Okay. But we don't have time for that, so we'll just go over a couple of examples and then show you the code. Okay. If you think about it, right, if I were giving you this task of implementing this function and you thought about it for a little while, you'd probably come up with the fact that, hey, doesn't this really mean that all I'm doing is finding what the median of the array is, right? And then kind of placing it in the middle, right? And that's correct, right? And in fact, that is, if you will, the ideal pivot that we would want to choose. But of course, we don't know what the median is, so we would have to spend computation time finding the median, okay? Which can be counterproductive, okay? But ideally, if we knew what the median was, that would be our ideal pivot for the partition, okay? Because by definition, in a median, right, you're basically splitting half of the array would be on the left-hand side of the median, and half of the array would be to the right-hand side of the median. Okay, assuming that we placed it in the middle. So this can be compute intensive, so therefore we can have simple alternative, which is to just pick any element, right? So statistically, that actually does not work bad at all, to just basically pick at random. Of course, because it's random, it's not guaranteed to be a good pick. So we'll talk about what happens when we don't have a good pick. Okay? In fact, we'll talk about the worst possible situation in terms of picking a bad pivot. But the thing is that the quality of choosing this pivot, okay? Remember, we're going to have multiple recursive calls, which means that we're going to have multiple calls to the partition function, which means that we're going to pick a pivot multiple times, okay? And if you average out the quality of picking such pivots over all the times that you're selecting a pivot, it actually comes out to the fact that picking at random is not that bad. Okay. So what we're going to do is basically pick random by picking the last, right? And that is the last element in the array, which we know nothing about its value. So if our condition is, all right, whatever is the rightmost element, that's what I'm going to use as my pivot, right? But again, assuming that the input array is in random order, then it's just as good as picking a random value from the array. If I just say that I'm always selecting the rightmost element of the range that I'm looking at. Okay, so I'm gonna say 6 right here is my pivot. Okay, and then I'm also gonna have then pointers here. Let's call this L for left. This one here, R for right. Okay. And what I'm going to do is I'm going to increase L, okay, as long as the value that I'm looking at for L is still less than our pivot, which is 6. Okay, so for example, L would start at 2. We see that it is less than 6, so therefore we increase it. Okay, to now look at 9. Okay, so let me actually change some colors here so that it's easier. Make this red for R. Okay. All right, so now I've moved L once, and I don't move it anymore because I see that L is now pointing to 9, which is greater than 6. Okay. All right, so then I'm going to actually try to move R. Okay. So we have R currently pointing to 8, and I'm going to decrease it while the elements that R is looking at is still greater than 6. Okay. So in that case, I move it here because 8 is greater than 6. Now R is pointing to 5, which I find is less than 6. So now I stop moving R. And what I'm going to do there is then swap what we're pointing currently at, right? So let me change this to black and I'm going to swap these two. Okay. So now what we have in terms of the results of the array is 2, 5, 3, 4, 7, 9, 8, 6. All right. So what this is trying to do conceptually is basically have a pointer on the left side of the range that I'm looking at, and then have a separate pointer on the right-hand side of the range that I'm looking at. Find, basically, call it a candidate to swap, right? Basically trying to find an element on the left-hand side that should not be there, right? That's what we found when we got to 9. Similarly, on the right-hand side, I'm trying to find an element that should not be at the right-hand side. In that case, we find it to be 5, and then swap the 2. And you might be thinking, well, wait, 6 is still on the right-hand side, okay? And that is true. So what we're going to do at the end then is basically swap our current pivot, okay, with L, right? But first we kind of need to finish iterating over or finish moving L and R. If you keep going here, you would see that effectively the rest, so this section right here, so I won't do it step by step, but this section here, basically you would find out that there's no candidate to swap except for 7. But then you would have no candidate to swap with on the right, which would be this section here, right? But we'll do this step by step when we show the code. So at that point, the way to make this work is then swap 7 and 6. And you'll see that that way we'll get the following: 4, 6, 9, 8, 7. Okay? And sure enough, we see that to the right of 6, everything's greater than. To the left of 6, everything's less than. Okay? So no worries, we will show you code kind of explaining what's happening here. But just so you have an idea of what we're trying to do with the code that I'm about to show you, again, find some candidate that I can swap with on the left-hand side of the array. Similarly, find another candidate to swap with on the right-hand side of the array. Once we have those 2 candidates, I swap. Rinse, repeat until basically left and right get past each other. Okay. All right, and then, so that's a good example in a sense that when we picked 6 as the pivot, we did manage to kind of split the array roughly half and half, right? Where, the pivot, it's sitting close to the middle of the array, okay? But here is kind of the worst case situation for this particular approach for picking the pivot, okay? Which was, if you recall, just pick the rightmost element. If we happen to get as an input a pre-sorted array, then we would say, all right, so I'm going to select this as our pivot. And you will see that if you had, again, your left pointer pointing to 1, and then your right pointer pointing to 4, you would basically spend all the time trying to move right this way and trying to move left this way, and basically at the end come up with basically the same ordering in the array, right? So it's effectively wasted. You partitioned nothing, right? Because it just so happens that the input was already sorted, okay? So there's effectively no right-hand side here, okay? So therefore, there's no candidates on the right-hand side that you could swap with from the left to make a partitioning. All right, so that's the worst case scenario because your partition scheme is not doing anything. There's no partitioning happening. And you might say like, well, but it's already sorted, so there's nothing to do. Yes, but we don't, like the algorithm doesn't know that beforehand, that the input is already sorted, so therefore it would spend the time and so waste runtime doing this. All right, so that's basically an overview of what we're looking to accomplish. So now let's look at code for how to do this. So this is what it would look like, right? So basically, we have this first line, which is the part where I am selecting the rightmost element in the current section of the array that we're looking at, that's given by left and right, right? Notice that the less, the minus minus right here is to the left of the right variable. So therefore, the decrementing is going to occur before the assignment to pivot. Okay. So this is choosing our pivot as the rightmost element in the section. Then we have a while true, which is, easier to look at and explain here, but there are better ways to write this so you don't end up having to do a while true, because that looks funky. But for now, we're basically going to say, all right, while true, this section of code is find candidate, find left candidate, to swap. These are lines 4 and 5. Then here, I'm doing the same thing, find right candidate to swap. Okay. Then if I get past each other, I'm done. That's line 8 and 9. Okay. I'm done. I would break. And then once I find those candidates, I go ahead and swap those two. Okay. Now, at one point, I'm going to evaluate line 8 to be true, right? At some point, this will happen, which is that left is going to get past right. At that point, I would break from this loop. And then all that remains is to place the pivot where it belongs, given that I've done all the swaps that I needed to do. If everything has flown correctly in the previous two while loops and the swap, then it would mean that all I need to do is swap the value that sits at pivot and swap it with what left is currently pointing at. Okay, and we show that in the previous example. And that's effectively how it works for partition. All right, so you might be not pleased with line 2, where we're basically selecting a pivot as the rightmost element in the array. So, before I go there, here's a quick overview of what I just explained with my terrible writing. So I'm just going to erase my terrible writing if I can. And there it is, right? So we choose last item at pivot. This is line 2. This right here, lines 4 through 7. This right here is line 10. And this right here is line 12. And then remember that our the context in which the partition function is used, which is Quicksort, is expecting that this function returns the index for the pivot, which at that point it would be left, right? Because of the previous swap that we did in line 12. Now the pivot value actually sits in left, so I would just return left. All right, so you might not be comfortable with line 2, that is choosing that last item as pivot or the rightmost element as pivot. We will discuss other ways because, again, with this particular methodology for picking the pivot, we already saw that there are particular situations in which the partition would just be wasted, right? The call to partition would be a waste because if it's already in sorted order, again, the sorting is ascending that we're looking at. If it's already in that order, the partition function is not doing anything, just a waste of time. So we want to say, all right, so let's do better at picking our pivot. What would that look like? Well, one approach is to say, well, I'm just going to, again, it's effectively picking at random. So I might as well say, I'm going to pick the pivot as the middle. Okay, sorry, I lost my pen. There we go. Let's say, given the range by left and right, I'm just basically going to pick whatever sits at the middle of the array, right? So rather than selecting whatever sits at the rightmost part of the array or the range that I'm looking at, I'm going to pick the middle because it should be just as good. Okay. But because I'm doing that, then I kind of have an extra swap that I need to do, and then because we need to actually move the pivot to that point to the rightmost position, and then we set the pivot, and then everything else would just go about its business, right? The rest of the code is the same as what we had in the previous slide because we basically moved what we selected as a pivot to be as the rightmost element in the range. Of course, you can say like, well, that's kind of a waste. Why don't I just straight up also not move it and just keep track of the fact that it's actually there? Yes, you can do that, but then that will mean that the code from line 6 to 16 would need to change. And so we're trying to keep it simple. So we did that just now, just so the code from the previous slide doesn't change. Okay. All right, so this is what we're doing here. Choose middle item as pivot, swap it with the rightmost element, and then repeat as before. So this is line, I would say, oh, it's line 2. This one is line 3 to 4, and then the rest is line 6 through 16. All right, so time analysis for this, right? So, and this is interesting because even though we have nested while loops, if you recall from the previous code, in fact, we had a while true, which is oftentimes not something that you want, but it is a couple of nested while loops, but this runtime is actually linear, right? And that's not hard to see because basically all we're looking to do for the while true is to determine when do we need to swap, and that's it. And definitely the number of swaps is bounded by n, so that's why the outer loop is going to run in linear time, and then the internal loops, all they're doing is moving pointers, right? So therefore, they're not going to be n times n. Okay? So in the worst case, which is that a pivot always leaves one side empty, so that is analogous to the previous example where we saw where for choosing the rightmost element, we had input that was already sorted in ascending order, and therefore it was kind of the worst situation, okay? Because our partition is effectively wasted. Everything would always be on one side of the array. So therefore, that gets you, if you did the, I'm sure everybody loves solving recurrences. If you come up with that recurrence, it would look like this. You spend the time for partitioning, which is n. You have one recursive call, which is for the left-hand side. And then the other recursive call would do nothing. So that's just t of 0. So basically, if you use substitution, that would come out to n squared. And you saw plenty of examples of this when you were talking about solving recurrences with Professor Paoletti. But in the average case and best case, which is when we select a pivot that roughly divides the array in half, right? So we pick a good pivot such that each recursive call is even in the amount of work that it would do, okay? In that case, what we have in terms of a recurrence relation is n, which is what you would spend on actually doing the partitioning, plus t of n divided by 2, because again, we're assuming that it does roughly divide the array in half, and another t of n divided by 2, right? So you have 2 times t of n divided by 2, and if you use the master theorem there, that actually gets you n log n. Okay? And the average case analysis, which would be actually really, really complicated because, again, you would have to assume some uniform distribution for the input array and then establish like Chernoff bounds and all that sort of stuff. And then all that it will come out with is that it's roughly 1.39 n log n. Okay? So again, O of n log n. So we're not going to go through that mathematical analysis because, we know better. And we'd have to spend kind of half a class describing that average case analysis. But we've definitely given you rationale for what that average case analysis looks like. All right, so what about memory consumption for Quicksort? Okay, so it requires stack space because it's a recursive algorithm. Okay, as I was mentioning earlier, the first recursive call is not tail recursive, so each time it will require a new stack frame. Contrast that to the second recursive call, sits at the end of the function. It's the very last line of code, so therefore nothing to remember when it comes back from recursion. Means it's tail recursive. Okay. So in the situation in which we have the bad pivot selection, what we can do then is basically pay attention to how big each half of the array that the partitioning is doing, right, or roughly half, how big each side is, and determine whether it's roughly corresponding to half the amount of elements that I have, right? And then detect the cases in which it's not, such that I can say that the larger section would go to the recursive call that is tail recursive. Okay, so basically, you would want to spend the non-tail recursive doing least amount of work, right? So again, this would look like if the stack frame is split, roughly everything's on the left and nothing on the right. Then you basically would like to avoid that if you can. And I'll show you code in the next slide that is looking to do that. And then on the other hand, if you have zero elements on the left-hand side and then all the elements on the right-hand side, then that means that because the right-hand side is the last recursive call, you would actually spend constant time in terms of stack frames as opposed to linear number of stack frames. Okay. So this is what the updated code would look like. Effectively all the same from the previous slide where we had our quicksort algorithm. Other than we're adding lines, this if statement right here, which is how we're choosing the order of the recursive calls, right? Based on how many elements I have on each region of what remains to be sorted. Okay. And so that way, what I'm trying to do is maintaining some balance between the recursive calls in terms of the amount of work that they each would do, such that allows me to satisfy the fact that I want both sides to roughly be equal to O of log n recursive calls. Okay. So again, the difference between lines 6 and 7 is just that they're swaps. They're swap in line 9 and 10. Okay. So you're shifting whatever is the largest section of the array largest section of the array that remains to be sorted, deciding where to send it off. Notice by the fact that this is an if-else. So here we have two kind of final lines to the function, line 7 or line 10, depending on what needs to be done. So both line 7 and line 10 are tail recursive. Line 6 and line 9 are not. Okay. So it's a matter of whether I decide that line 7 should be the last tail recursive call, or line 10, again, depending on how big the region of the array is. All right, so just like any algorithm, there's pros and cons to Quicksort. So some advantages, of course, on average, in practice, it's very fast. N log n asymptotically, but it can perform faster than that with not asymptotically, of course. Again, in practice, it can be quite fast. It has a short inner loop, right? It's just linear time. It is fairly efficient in using memory. Again, we're not creating any extra memory. Everything's in place, but there is the fact, which is a disadvantage, that you have extra stack frames. Okay. So another disadvantage is the fact that in the absolute worst case, okay, it's n squared time. Okay, but that is assuming a really bad pivot selection. So it's really a pathological case. You really would have to work at, making the algorithm behave in n squared time. Okay, we showed you an example of that when our selecting of the pivot strategy was kind of weak, right? Like, folks could potentially reverse engineer. In fact, this is true of any pivoting strategy. You could potentially reverse engineer the pivot strategy and then give the algorithm input such that it behaves in worst case complexity of n squared. But it's a lot of work, right? In order to be able to do that. So oftentimes, we don't have to worry about this n squared behavior. Partitioning is fragile. Simple mistakes will either segfault or not sort properly, right? That's what I was referring to when I said that, hey, there's not a lot of code, which makes it easy, but you have to be quite careful with what you're doing during partitioning, moving your indices, make sure that they're being moved at the correct moments, and they don't, make sure you detect that when they get past each other, you need to be done. Stuff like that, that if not taken care of, then it runs you into bugs and issues pretty easily. All right, so let's look. So far we've seen only one pivoting strategy, which is, again, selecting the rightmost element. I mean, as far as the strategy goes, it is selecting the pivot at random if you decide to use the rightmost element. But of course, it assumes that the input array is in random sorted order. So if you're giving an input where it's actually correctly sorted in ascending order, then it's going to behave bad. So let's discuss actually other pivoting strategies, if you will. Of course, in general, you would not want to spend too much time trying to select the pivot, because then it will defeat the purpose of the partitioning, right? In a sense, partitioning should run in linear time. And if we spend too much time selecting the pivot, then that might need, you might implement it in such a way where partitioning runs in more than linear time, which would be bad, because then it will defeat the performance of the entire Quicksort algorithm. So what would be a way to select a good split, if you will? Rather than computing the median, which again would be the ideal, but it would be too much compute time to do that, we can sample it. right? And in fact, in general, sampling is a very powerful technique. It's used in many randomized algorithms. So we won't see any other randomized algorithms in this course, but if you go to other courses like 376, you will see plenty of other examples of randomized algorithms where sampling makes a big impact. Okay. So let's look at some of the other pivoting strategies that we could use in the next couple of slides. What we can also do is to improve the overall performance of Quicksort is, hey, when, say, the small region or small section of the array that I'm looking at is up to a specific given size, k here, let's just not do Quicksort, right? Because doing Quicksort on such a small array, which is often, or again, small section of the array, which is often 16 or 32, is kind of a waste of time because it's so small that you can assume that partitioning won't do much at that point. Things, if you will, would be at that point fairly sorted. And so incurring all the costs of doing partitioning is wasteful. So you actually might resort to, when you determine that size is less than k, just use insertion sort. Okay, so that's another potential optimization here. In fact, that is what intro sort does. It basically based on some, call them heuristics. I mean, I wouldn't really call them. Let's call them best practices. Based on some best practices, the intro sort will select the proper sort to use. Okay, and I'll talk about that in a little bit. So here is another pivot selection strategy, right? So this is fixed sampling. So all I'm going to do is basically select the leftmost element, the rightmost element, and whatever the and then find the median. And then select the middle element, and then find the median of these three elements, right? Which would make the pivot here 14, right? Given this particular input array, 17 is the leftmost element, happens to be the leftmost element. 5 happens to be the rightmost element. 14 happens to be the middle element. I take a look at those three and take the median of those three, which in this case is 14. Okay. So that's sampling. We're effectively sampling from the original array, coming up with our really small array of just size 3 right here, and then taking the median of that sample. Okay. And that's constant time, right? We don't need a loop to do that at all. So that's constant time. So it's really fast way to come up with a pivot that's based on sampling and has been shown to be fairly effective. So another pivoting strategy is that, again, you select 3 elements, but there you select the 3 at random, right? So instead of selecting the leftmost, rightmost, and middle, you basically select 3 elements of the array anywhere they may sit, right? So you literally use the rand function in STL to decide which one of these indices you're going to use. Let's say the rand comes up with the indices to 1, 42, and 28, and then take the median of those 3. Okay, so again, haven't done much work here, so it's actually just constant time. No loop needed. Okay, and that's another particularly effective pivoting strategy. Okay, that is based on sampling. I encourage you to actually kind of take the code that we have for Quicksort in the previous slides and change it up to use your own pivoting strategy. and see how it affects the runtime. Okay, we've definitely given you tools to measure runtime, and we're giving you the algorithm itself. So it's up to you to kind of play around with it to see how it behaves based on different either input conditions or improvements to the algorithm. Okay. I would also encourage you to look up online the formal paper that has the average case analysis for Quicksort. In fact, I believe it's in CLRS as well. I encourage you to look at. It's very mathy, but it's interesting if you like math. All right, so in summary, we have Quicksort as being, on average, an n log n algorithm, sorting algorithm. Its efficiency is based upon selecting of the pivot. Notice that selecting of the pivot is so important that here we didn't really refer as like how many number of comparisons or how many number of swaps were we doing. It would be, or it would be somewhat useful, and you could definitely construct an analysis of Quicksort based on number of swaps and number of comparisons. But all of that analysis would kind of be overshadowed by the performance of the algorithm if you don't really look at how you've been selecting the pivot, right? The selecting of the pivot is so key that we basically disregard everything else in terms of comparisons and swaps, and we really focus on the selecting of the pivot in order to understand the performance of Quicksort. And we said that, interestingly enough, just selecting a pivot at random works fairly well in practice. We looked at other sampling strategies for pivot selection, where you would just sample 3 keys. And there's actually plenty of other creative methods. That's another interesting thing to just look up online, pivot selection strategies for Quicksort. So we looked at other methods for tuning, which was make sure that if we have a large section of the array, make sure to make it the tail recursive call. Okay, that's another optimization that we looked at. What STL does is actually, when you call the sort function, is actually more in line with what we've been calling intro sort. Okay, intro sort stands for introspective sort. So you've heard me talk about it in previous lecture. Basically, it's the notion that it's introspective, right? It basically takes a look at the input array, and based on some metrics, it decides which sorting algorithm to use. So effectively, if the region is small, so if the current range of the array that you're looking at is small, and we described earlier roughly what that, say, might be 32, I think it's what I've mostly seen. You might as well just use something like insertion sort, which is an elementary sort. But because on such a small portion of the array, given the previous partitioning that we've had in Quicksort, because if you see here, it says else use Quicksort, that small section of the array would be close to sorted, right? Given all the partitioning that we've been doing. And so we might as well not spend the time doing recursive calls and then just pass it to insertion sort. Okay? Else if recursion depth is too high, okay? Which, to be honest, I mean, I don't know the statistics on it, but I would assume that this happens fairly infrequently, that you get a recursion depth that is too high. You would use heap sort instead, okay? Otherwise, you fall back to the default, which is using Quicksort, right? So if you can imagine, every time you call STL, it basically spends a bunch of time doing Quicksort, and then at some point, it'll switch to insertion sort, okay? Again, we have this else if the recursion depth is too high, use heap sort, but to be honest, it doesn't happen quite often. All right, so in terms of sorting algorithms, and again, we have one more sorting algorithm to discuss in the next lecture, which is merge sort. These are roughly the large-scale classification in terms of big O. We have bubble sort, insertion sort, selection sort. These are your elementary sorts. That's how we've been calling them. These are worst case O of n squared time. Then you have your high performance sorts that we've discussed so far at heap sort, if you remember back in the heap lecture. This has a worst case of n log n. And Quicksort, which is a divide and conquer algorithm. More on that when we discuss algorithm families in a lecture after the exam. Okay, it is divide and conquer, but that just comes from the fact that we're looking at one section of the array and making a recursive call only on that section of the array, and then have a separate recursive call for the other section of the array that remains. So that's in practice divide and conquer. So on average is also n log n, okay? But of course, as we mentioned, quite dependent on pivot selection. Memory usage, real easily, we saw that bubble sort, insertion sort, and selection sort was most definitely in place because we never had to create an extra array for anything, okay? So everything, all the moving of elements happened in the same input array that I was given. But how about heap sort and quicksort? Anybody want to say whether heap sort is in place? Anybody? I'll wait on the chat if anybody wants to mention whether heap sort is in place. Give it 10 more seconds. Well, actually, we're doing quite well on time today. So heap sort is in place, I believe. That is correct. It is in place. If you recall back to the heap lecture, probably the last slide or close to the last slide, we showed you code where, by way of usage of the, if you recall, the heapify function, we were able to do it in place, right? So we did not need to create an extra array. In fact, we did describe a heap sort algorithm where you could use a separate array, but it's wasteful because you have heapify, and all you would need to do is pop every element in the constructed heap, and so everything remains in the same array. You use swaps, right? So go back to that lecture and look at the code. And then quicksort as well is, as we saw today, is in place. We never had to create a separate array. It all happened in the same array, but do pay attention to the fact that quicksort is recursive and therefore there's stack frames. So we talked about that as well today. Okay. So, but in terms of classification, we consider quicksort in place, even though there's the extra stack frames. Okay. All right. How about stability? This is an interesting question. Hopefully, you all remember in the previous lecture how we define stability, right? If there are two elements that you're looking to sort that have the same key, right, which means that the comparator is going to say that they're equal, the order in which they come out of the sorting algorithm, right? So if one element came before the other one, is the same order in which it was given as input, right? So the order they come out, same order that were given as input, okay? Of course, if the keys are not equal, then they're not going to come out in the same order. But if they're equal, we assume they're going to come under. That's stability, right? All right, so let's say by way of hands, or sorry, this is what I usually say in live lecture, in-person lecture, but we can't do live, hands here. Is bubble sort stable? Can anybody? So heap sort and quicksort are both in place. Yes, they're both in place, but quicksort kind of has a caveat with the fact that it's a recursive algorithm, and therefore it does incur extra space in terms of stack frame, right? All right, so we have bubble sort as being stable, right? If you go back to the code, it's based on swaps, right? So if the key was to the right of, say, the current key, and they're the same, then you just don't swap. So they stay in the same relative order, okay? Insertion sort, if you go back, you'll also see that it is stable, right? And in fact, also selection sort, oh, well, excuse me, is selection sort stable? Give it 20 seconds. No, so Kevin Chen says no, that is correct. It is not stable. Okay. Now, the trick question is why? Why is it not stable? What can you say about this algorithm that would point to the fact that it is not stable? If you remember what the algorithm does conceptually, that should help you understand why it's not stable. So I'll just go right ahead and say it. Not necessarily because it keeps swapping. If you recall, the inner loop in selection sort, its job was to find the next minimum element that should be placed in the current position that the outer loop is looking at, right? So in that min function, it's going to depend on which element it actually finds first, right? As it's trying to find a min element, right? And so that's why it's not stable. There's no guarantee that when that inner loop runs, it's going to find the element in the same order in which it was given and placed in the output in the same order in which it was given as input. Is heap sort stable? The answer here is, I'll save you the suspense. It's no, but the question is why? So yes, underrated said when you select something, you swap it into the correct place, but whatever was there already might get mixed up with another element in the same key. Yes, correct. That's probably a better way of describing what I mentioned earlier. All right, how about heap sort? Why is it not stable? All right, in the interest of time, heap sort is not stable because it basically relies on a heap, right? Actually, if you recall to the heap lecture, we mentioned the fact that even the container, so make it a vector or an array that we're using behind the scenes and that you're implementing in your projects, right? The vector that sits behind the scenes, we cannot claim that it's an ordered container, if you recall, because given that we want to keep the heap order property and we have the fix down and fix up functions, those functions might mean that it moves and shifts elements around in the array where they might not come out in the same order in which they were given as input. Okay, so basically the summary here is because it relies on a heap. Okay, and then how about quicksort? That is not stable. In fact, it's quite hard to make stable to the point where if you wanted a stable sorting algorithm, you do not want to use Quicksort because it's quite hard to make stable. But this one is no, because it relies on the partition function. Okay, and if you look at how the partition function works, there is no guarantee that we're not going to shift things around to the point where they come out in the same order they were given in if they have the same key. Okay. All right, so we finally managed to finish in time for the lecture today. Here are some questions for you to study. I'll leave them as open questions for you to look over, and come to lecture Q&A office hours if you want to find out the answer or more information about the answers to these questions. But do go over this actually before the exam. It's always good practice to look at these questions and the answers before the exam rather than after. Okay. What do we use if we want it to be stable and quick? All right, so good question. So we're going to talk about that on Thursday, like we already have on the chat when we talk about merge sort. It is a quick and stable algorithm, but there is a downside, and it does rely on extra space. But space nowadays is cheap, so I mean, back in the day, space, memory was not as cheap, so that was particularly important. But I mean, now you get laptops with many gigs of RAM, so it's not too bad. But yeah, so we'll talk about that Thursday. Why is stability good? So good question. It kind of depends on the context of the things that you're trying to sort, right? So I'm trying to think of a particular example where that would be important. But it's really, there's a bunch of contexts in which it would not be important at all. Like you wouldn't care, right? It can be important. I failed to think of an example right now. I'll take it as a note to give you one on Thursday. I don't know if whoever is on the chat can think of a quick example. I know I've had this question before, and I always had an example ready, but for some reason I'm forgetting it. So we'll talk about it Thursday. All right, so that's it for today. I will sign off. Again, encourage you to visit our Profis Hours and Lecture Q&A. And we also have replay Q&A, again, where look it up on the calendar, on the lecture calendar, by the way, where we'll have faculty basically look at bits of lecture video and then immediately run through Q&A. Like stop the video and go through Q&A with all of you or whoever is interested in doing it. All right. So, all right. See you all, or I won't really see you, but let's connect on Thursday. Have a good evening or rest of your day.